this is our final design review for L3Harris secondary mirror support structure. Um, Here is our team member. So in the picture from left to right, it's Caitlin, Angel, Matthew, Stanley, and Joshua. And so this project is trying to redesign the secondary mirror support structure using 3D metal printing, and we're trying to reduce the manufacturing time and cost while still maintaining its strength. So we've also tried to implement a internal lattice within our structure to try to reduce its weight while still maintaining its strength. So secondary mirror support structure is a mount used in space telescope to hold up optical mirrors, and so if they have to be really highly durable and very precise, since we're capturing light from probably light years away. And with increased durability and precision, it also comes in increased production time and cost. So we're trying to use additive metal manufacturing in order to reduce the cost while also maintaining its strength and production capacity. And these are the deliverables and requirements provided by L3Harris. So it has to be fingerprintable. It has to hold 23 pounds of equipment. It has to interface with the FMS at 3 locations of 120 degrees apart. And there are a couple of factors of safety that we should meet. And here is on the top right, here is a simple schematic of how the space telescope should look like. And mainly we're focusing on the top here for our secondary mirror support structure. These are our specifications for our project, and more notably, we need to have positive margin of safeties at the specific load and temperature range. And of course, we need to have a displacement under these thermal loads for translation and rotation. And let's talk about our work breakdown structure and critical path management.
So for our initial work breakdown structure, well, this is it here. So we generally followed this fairly well. However, there were a few things that came up which made it so we had to change this slightly. So just focusing your attention firstly to the final CAD model. In this structure, we didn't place enough emphasis on the optimization. So we did lots of topology optimization and also lattice optimization, which we didn't fully account for in this. And then also for our testing, we initially thought we were just going to be doing 4-point bend tests, but we had to change it and implement the 3-point bend tests as well. But everything else is kind of fairly consistent with what we did. On to the next. So this was our initial kind of like budgeting about how much we thought the project was going to cost. So this was quite a severe underestimation of kind of the hours we were going to be committing to the project. So we said in this at the beginning that we were going to be spending around $18,800 on labor, which is at $100 an hour. But instead it's worked out around $70,000. So it's a lot more expensive than we initially planned. But this is definitely a learning point. So this is our critical path that we did at the beginning, and again we stuck to it to some extent. But as I mentioned before, there was other things that took longer than we expected, and also new things that arose. So we didn't fully stick to it strongly. So next up is the initial design process. So we'd created a puck matrix at the beginning, comparing last year's design, Stanley's design, and Joshua's design. And then we came out to a total saying that Joshua's design was the best design that we had at the time. So we went ahead with this design. So throughout the project, we did lots of testing on sample coupons. So we did, testing with different lattice types, different materials. So we used the fused deposition modeling, FDM, to make the ABS and PLA samples as shown on the bottom. And then we also got some aluminium test coupons, which were made using the powder bed fusion. And we're also using this method for the final design, which is due to come in today.
So next we're going to go into the coupon testing. We did a few iterations with this. So the first set of samples was the 7-inch long ones. They had different lattice inside because we're testing out the different ones. It was the bitriangle, the dodecahedron one. And from the first round of testing, we did the 4-point bend testing setup. As you can see, there's like the 2 upper supports, 2 lower supports, and then we had a load come down as 1100. At the bottom left, sorry, it's kind of hard to point. But yeah, so this was just the first set, and then we have a few other iterations, specifically honing in on the dodecahedron lattice infill, and then another set with but making them smaller, so 4 inches, so they're faster to produce.
Yeah, so like Angel said, we started originally with the 7-inch models, and then we reduced it to the 4-inch models so we could print more of them and test them more rapidly. And then we also ordered the aluminum coupons in the 4-inch, so we wanted to validate the test procedure with the 4-inch models instead of the 7-inch, just so we could just move like smoothly to the aluminum ones. So basically, for the method of how we calculated the stiffness for each of the samples from the testing, we took the force displacement curves from the MTS machine, and we identified the linear region, and this was also visually identified, so there's room for error in that. But yeah, we found the linear region, and then we calculated the stiffness from that, and then we also modeled the results in NX, or we modeled the same 4-point bend testing in NX. First, we started out with the 7-inch samples, and then as you can see, we got a pretty high percent error between the tested and the simulated results. It was like a 57% error between the two for the stiffness, and pretty much the same for the mass. So we saw that they were doubled, and we had to sort of like narrow down on that and why it was pretty much like the stiffness and the mass were doubled in the simulation when compared to the tested results. If you could go to the next slide. Thank you. So then we determined that when we made the part, we actually shelled the model twice. So there was a shell in the creation of the part file, so that's like 0.05 inches. And then in the FEM, we also shelled it again in the 2D thin shell connection, which was also 0.05 inches. So it was shelled twice, which increased the stiffness and the mass by double that of what it should be. So then we edited the model. We had to figure out sort of how to remove this extra shell in the part, but also to make sure it resembled like the open model that we had in real life. So it was a bit tricky, but then once we figured that out in NX, the percent error between the stiffness was a lot better. It went to 24% instead of the 57% that was seen previously. But then there's still like the percent error was still pretty high between the two. So we had to sort of hone in on what was really contributing to the discrepancy. And we were determining that the Young's modulus for ABS was different in NX than what we were using for our like metal or for our ABS coupons. So the way we determined the Young's modulus was that we 3D printed another coupon to test with. So this one was it's in the top right corner. It's just like a thin rectangular beam made of ABS as well. And this one is not shelled. It's completely solid. So we put it through the same 4-point bend testing as the previous models. And then we got the force displacement curve again. And then we calculated the Young's modulus with this equation that is used for 4-point bend testing. And then once we got this Young's modulus, we used the same modulus for our other, like the 7-inch models that we did previously. And the percent error was drastically reduced to under 10%, which is considered acceptable. So that was definitely an improvement. And then after that, we moved to the 4-inch ones. So that was all but the 7-inch. And then we felt more confident in our results after we got the Young's modulus, and the results for the stiffness were much closer between the two. But then we moved to the 4-inch models. And then this is what Angel was saying before. We originally tried the 4-point bend testing, but then the top and bottom supports were really, really close. And it led to stiffness data that was like very much wrong no matter what we did. And that's like due to that shearing instead of like an actual bending force applied. So then we switched to a 3-point bend testing setup, and it's like all the same parameters. We had the same load applied. And then the bottom two supports were once again 0.5 inches away from the ends of the model. And there's like the picture in the bottom left. And so we did the same thing where we simulated the 3-point bend testing in NX. And this was a bit difficult to get to get right. So I had to do a lot of figuring out like the mesh density size, like the mesh element size. So originally it was 0.125 inches. But then it was really interesting because it wasn't, it was spanning over elements that shouldn't have been in the mesh. So I reduced it to 0.05 inches. And that improved like drastically. So then we got the stiffness to be 2.62% error between what we simulated and what we actually tested. And this was for the 4-inch models that had the dodecahedron lattice, because that's the lattice that we were focusing on. And they either had 0.07 inch rod thickness or 0.06. And we were, after like we did this, we were pretty satisfied that, you know, our NX simulation of the 3-point bend testing was going to yield what we expected from the test results. So then we were like, we felt pretty prepared for our aluminum coupons that we ordered and came in. Unfortunately, they didn't have the same lattice as the 4-inch models did, like the 4-inch ABS coupons that were shown earlier. But we still did the same 3-point bend testing on them just to see if the results would correlate between the two. So I also simulated this in NX as well. And we also did X-ray spectroscopy on the models as well, because the box, so I'm pretty sure either the box said it was aluminum, but then like the vendor invoice also said it was stainless steel. So we were kind of confused on what the properties actually were, what it was made out of. So we did the X-ray spectroscopy with Chris Pratt, and we saw that it was only 80% aluminum when it should be like 100% aluminum. So that was a little disappointing. It was made up of a bunch of different elements. I mean, the highest was carbon and silicon with like 7.8% of the percent weight. So that we had to take that into account when we were like comparing the two, like simulation versus like the tested coupons, because in NX it's like fully aluminum. It's like the idealized model. And then we also, from the microscopic imaging, we saw that the shell thickness like isn't exactly the same on every single side. So there's like, it's like kind of sloped, if you can like see in like the leftmost image, and also like the right one too. You can really see like how it's like variable, and it ideally would not be like that. It was, we were hoping it would be like completely like the same on all 4 sides. So when I was running these in NX, I pretty much just like took the average of the thickness, because I obviously like couldn't like model like the sloped edges. And so comparing like the stiffness again, I actually got like pretty decent results, but the mass percent errors were higher. And I was attributing that to the fact that they weren't entirely made of aluminum like we expected. But at least we were still getting, you know, results that were somewhat still like decent, like correlation between the two.
All right. So the other big thing that was a huge learning curve for us was figuring out how to set up a model that we could optimize. So we took the initial design, cut it into 6 pieces so that we could work with a 1/6 version. Then we took about 2 weeks to learn how to set up a method of mimicking symmetry on the 1/6 model so that it would behave as if the entire model was there. We then did some validation for that. We took the 1/6, mirrored it radially, and then tested sort of the max displacement, found the values were within 1%. So we proceeded with the 1/6 model, and we ran a couple solution 200s in MATLAB, as they're called. MATLAB, geez, NX, excuse me. And we ran 2 different methods of optimization, or 2 different goals of optimization. The first one being optimizing for isothermal displacement. The second one being optimizing for weight, and using the load that produces the lowest margin of safety. So with the temperature, with the isothermal optimization, we basically found that the lattice has no effect, yay or nay, on displacement as long as the part is fully symmetrical, we had displacements on the order of something to the negative 12 inches, which is effectively 0. So we ran those pretty quickly and then kind of moved on from that. The big one was doing the load-based optimization. For both of the models, we used a lattice and shell range, with the minimum being the minimum print thickness we were allowed, and then the maximum being sort of an arbitrary value that we just assumed if it gets much bigger than that in the arms, you're going to have kind of mushing and interference, right? You're not going to see a shell versus a lattice. It's just going to be some weird air gaps. So we kind of set that as a limit. And from that load, we found that the lattice should, at least the solver said, the lattice should be the minimum thickness we told it to do, and the shell could be reduced to about 0.07 inches thick. On the next couple slides, we've got the results from the lattice optimization using the thermal loads. So as you can see, right, on the lower table, the solver defaults almost immediately to the minimum thickness we gave it. So we were like, maybe the lattice doesn't matter. So we ran it again on the next slide. And as you can see, it immediately defaulted to the minimum thickness. So, right, this is kind of saying, okay, at least for the isothermal load, the lattice doesn't really matter. Unfortunately, when we ran the load, the big load, that is when my computer died. So I don't have good pictures or any pictures from that, but we at least were able to get the data before my computer gave itself an aneurysm. But that was most of the optimization stuff that we did.
So furthering on from that, we also did topology optimization to get an optimized shape to the design. So we ran studies on max stress and max mass. And because you can only include kind of like a more simplified load, we just did the equivalent of an 18G load vertically in the Z direction. And we used constraints such as overhang angle, rod diameters, rotational symmetry, and construction bodies. And then for the max stress optimizations, we also put in a mass target as well. So by going through this, we slowly got to some more optimized shapes, which we then integrated into Joshua's design to try to get to this final design that you can see on the right. The image on the left is just an image of one of the final topology optimizations that we did.
All right, I guess we're. Oh yeah. So sorry. The last optimization we did was kind of after we had settled on a final design. The issue we had found is that the two beams in the center that hold up the actuator expand, and that leads to most of the isothermal displacement. We didn't see that in the symmetrical model because we didn't include those two beams, because then it wouldn't be fully radially symmetrical, which is why we didn't see this as an issue until we had a finalized model. The issue is because the initial model wasn't radially symmetrical, right? The lattice wasn't applied radially symmetrically. We attributed the too much displacement to the lattice and not the beams. So we did not assume that the beams would be an issue. We assumed the issue lay in the lattice, which was clearly inaccurate. So we did go through and we tried to change the geometry a little bit. On the next page, again, I had computer issues, so unfortunately I could only do rough sketches. I couldn't get actual pictures of the geometry because almost every time I would run these, for some reason, the computers in Retina started to crash. So I could never really get good images, but the result that at least isothermally had the lowest amount of displacement was the second from the left, the one with the perpendicular beams, if you want to go back to the previous slide. So at least for the isothermal displacement, the design that adds 2 perpendicular beams to the actuator mounts decreased the isothermal displacement the most. We did not have time to run any additional simulations, so we don't know if this hurts the vibrational mode or if this decreases our lowest margin of safety. But we are also adding more weight, which was one of the factors. This one ended up not being the heaviest. I think oh no, I'm sorry. This one was the heaviest. So that's the other issue. This brought our weight up by almost 0.8 pounds to about 17.7. So that is gonna for future work on this, that is gonna be something to bear in mind. For our final design, mass 16.9 pounds, first mode of vibration just over 120 hertz. The translational displacement is about 9.3 microinches, and rotational displacement is 0.53 microradians, so off by more than a factor of 10. The buckling modes for both with and without the lattice hover at around -0.9. Okay, so this is the ultimate and yield margin of safety. The lowest margin of safety was low temp yield, which is about 0.48. If you include the lattice in there, it drops down to about -0.6. So what that tells us is, at least yield-wise, the overall model will not yield, but the lattice probably will. So that could we thought that could present some potential stiffness issues. Some other sort of qualitative results is that both with the buckling and with yield margin of safety and vibration, all of that is happening in the z-axis. It's not really in the x or y-axis that much. So that is really where the structure is weakest. Additionally, this is something we were not able to determine the cause of, but no matter what what constraints you had on, no matter what you were using to report the margins of safety, lattice versus no lattice, high temp versus low temp, every margin of safety was on that one point on the actuator mount beam. So because we had such a difference of margin of safety, lattice versus no lattice, our thought was, okay, when we do lose the lattice, right? Since the lattice yields before the part does, when we lose the lattice, how much does the part suffer? From what we found, there's only a loss of stiffness of about 430 pounds per inch, which compared to the average stiffness, which is 43,000, we felt was negligible. So it seems like the lattice, at least this particular lattice in this particular geometry, it seems like it's little more than just dead weight. We went back, ran some additional simulations to change the thickness of the lattice to see if that could improve the stiffness. It did, but it also drastically increased the weight, and it reduced the part's overall strength to weight ratio. So what we can take away from this is that in this particular case, with this geometry and this orientation of a lattice and this type of lattice, it's not worth it, except to make printing easier, right? Because with the lattice, we don't have to do what the last year did, which with the weird overhang stuff, the weird angled bottom, we don't have to do that. We can just print it straight up because the lattice is providing that support. But pretty much once it's printed, the lattice is kind of like printer infill supports. It doesn't help much. Another thing that could be tested if we had more time would be change the edge length, which is sort of the size of the unit lattice. If you make that smaller, that'll probably increase stiffness, but again, it'll also increase mass. So it seems like there's a pretty hefty price to pay for increased stiffness, that price being increased mass.
My turn. All right. So this is what our final model looked like. Again, this is a butt joint when we just did the 24-hour epoxy, which is the black spots that you see. So we ran two testing, two different types of setups, or two different types of testing. Sorry. The first one was vibration testing. So as you can see on the right, so we put it on 3 different bungee cords, and then we went ahead and put an accelerometer in the middle, and then we just tapped it with a hammer. Very similar setup to last year's vibration testing. We have Muir keeping watch while we do this. And then on the left-hand side is our simulation value, which is like 87. Sorry, it's a little hard to see, but it's 87 hertz for the fundamental frequency. And then from the data collected from the vibration testing, we got it was not about 91 hertz. And then this is the stiffness testing, which is our second one that we set up actually later that day. So we ended up doing is that we kind of just put the model on like 3 simulated rollers, and then we put some planks so we can have like the weight rested on them. And then we just put 50 grams right at the center, and then we measured displacement using that gauge on the top right. And then from there with the displacement and the force, we found the stiffness, and we have the percent error of 2.2%. So this is the project conclusion. So this is just a table full of like all the different recs and specs. If we pass or we didn't pass, again, just going back to the last 2, we failed in the isothermal loads, but everything else to see we were able to pass those recs and specs. We're considering, so we're not completely eliminating the lattice. We're not going to just say no. I think it's just for this specific purpose, the way we set it up, again, with just a dodecahedron. And there was a lot of trial and error, even just implementing the lattice in NX. So we just said to evaluate a little bit deeper into the trade-offs and figuring, again, the edge length, if we can change it up a little bit, even if they can try different lattice types or different directions, because again, the stiffness is different in each of them. They bring different things to the table. Also earlier communication to the vendors, so they don't end up where we are and things kind of just get delayed and keep getting pushing back. So we're hoping that they implement it a little bit earlier in the process. Just even like immediately once they get just like a rough idea, just send it out. Just be like, can you do this? Can you not? Again, going back to, we're hoping that maybe they can go back to 2024, so last year's team, and looking at that because those arms were there for a reason. Like Mir pointed out and during our presentation, he was like, maybe we should have taken a little bit more consideration on the arm geometry because that was a big thing that they discovered last year. And then the very last one is the geometry of the actuator mounting beams would be an area that they would like to focus a little bit more on in terms of optimization and probably even try to find a way to test them, simulate them individually. And then, yeah,